I'm going to report results from an expedition in the Beaufort Sea that we had about 15 months ago. And we had a science party of maybe 29 people. And so far, just a few of us have been working as a team to try to understand some of the basic things we were funded to do. In the long run, there's going to be a lot of integration, I hope. And I do want to acknowledge all of the members of the science party, because you just can't go up there and do the kind of coring we did with a handful of people. My proposal, which was written a few years ago, was stimulated largely by the Merton et al. Paper. What you see here is one of the biggest hoses in the whole hosing world. And the thought is that there must have been a northern route to the glacial lake Agassiz discharge, and it's an old idea, but it's gained some traction in recent years by modeling and other things, and especially this paper by Merton. They propose a rather complex sequence of events with ice retreating and gateways opening and gateways closing and lakes recharging to account for two abrupt freshwater discharge events. The oldest one centered on 13,000 years and quite precisely dated, and the younger one more broadly dated. The thought is the older one would represent the trigger, the flood that triggered the Younger Dryas, and the younger one would be associated with the pre-boreal oscillation. Their age control is from optical dates, which I don't know much about and I can't defend, but the really remarkable thing is that they did 10 years of field work here in a region where, as Neil Driscoll says, the mosquitoes are large enough to carry you away. So they did some heroic work, and what you see where the terrain is marked in red up here and here in this area called Richards Island, you see flood deposits that are 30 meters above, as much as 30 meters above sea level. And often you see the first flood, and then you see dune sequences, and then the second flood. And the floods are marked by erosion features and large boulders. They also noted offshore channels leading out to the shelf break that would have been paleo channels that delivered fresh water directly to the Beaufort Sea. So we sailed from lovely Barrow, and not knowing too much about what conditions we would face, we kind of hopscotched all the way down to here. The sediment cover is pretty thin in Amundsen Gulf. Actually, down to here, we got a good core here. And then we filled in the gaps going back to Barrow. And at several locations, we double cored, as you can see here, for example, and here and here. And generally, the second core is longer than the first because we were feeling more confident with the coring system, and it worked very well. This was on Healy, Coast Guard's icebreaker. And the great majority of the talk is going to focus on these two stations here, stations 9 and 5, where we have two cores called 15 and 27. And the key feature that guided us, besides the seafloor bathymetry and the seismics, the 3.5 kilohertz especially, the key thing that guided us in our work was the magnetic susceptibility. And a lot of credit goes to Brendan Riley from OSU, who managed the logging van and collected some really great data. And this is a composite then of core 15, which stops here, and core 27, which has a very similar record, and we just patched 27 onto 15. And the point where they stopped was a very prominent, or where 15 stopped was a very prominent reflector here. So this is the magnetic susceptibility record of 15 with a sound velocity of 1,300 meters per second, which is exactly the sound velocity measured in the cores. So on this basis, we sort of rejected the placement of these two, and note that the high susceptibility intervals correspond to the bright reflectors. so we have high quality data from all of these cores, and there's some notable things, I think. And the first is, if you're close to the Chukchi Sea, you get very long Holocene sequences. And we define Holocene here kind of arbitrarily as the point above the first or the shallowest maximum in magnetic susceptibility. In fact, this only shows about half of the new cores, and it ignores a core we took in 2002 right there where we have 19.5 meters of Holocene. So it was really funny. For a long time, people were searching in vain for Holocene sediment in the Beaufort and Chukchi, and it's all along the slopes. And most of these cores are between 400 meters and about 1,000 meters. Again, the key cores right here, which you see right here, JPC 15. Now, this particular susceptibility record doesn't have the lower section where we've patched together. And you see, as you move in this direction towards Mackenzie, the thickness of the Holocene decreases and the thickness of the deglacial section increases. Now, bear in mind, the Holocene is roughly 10,000 years, and what we're talking about here is really only a couple of thousand years of sedimentation. So there's a whopping sed right here, and we'll talk a little bit more about that in a couple of minutes. You can also see that we have this expanded interval here between this magnetic susceptibility peak and this one here. We see it here in this section, and it may be this shorter interval here at this particular core. And as we go farther west, of course, we didn't penetrate deep enough to pick it up in magnetic susceptibility, but it does look like the reflectors during the deglacial interval are converging as you go farther to the west, indicating that the source of sediment, deglacial sediment, is this region here. And Neil Driscoll student Shannon Klotzko is giving a presentation on the grain size and the seismic stratigraphy at these sites in a poster session this afternoon. So I urge you to see that if you're interested in more detail. We counted lithic particles. After great thought, we chose 425 microns because we had a sieve that size. Smaller sieves would give us a great abundance of grains and wouldn't tell us very much more information, and larger sieves might alias the signal. Again, this is core 15, and you see a big spike here, and this is the upper, then this is equivalent to the upper magnetic susceptibility maximum, and this is the lower one. As before, we've patched, so now you see the record from core 27, and whereas core 15, which ends here, has only one little, that might be the spike, and whereas this looked really large, when you add core 27, this is obviously the most prominent event, using lithics as a proxy. Now I may slip up and sometimes call this IRD because it's convenient and it's a name we use in the lab all the time. But it's really, in my view, it's very complicated to look at Arctic sediments and figure out what's ice rafted and what's riverborne, because of course the ice is there every season, and riverborne sediment comes down and it can get picked up by the ice. And in fact, during the spring flood of Mackenzie River, the ocean is still frozen and the seawater just runs right across the ice. So it's easy to imagine how riverine-derived sediment could be transported by ice. So yeah, it's ice rafting, but when we talk about ice rafting, at least I have a North Atlantic perspective. I think of icebergs, but here it could be sea ice transporting river sediment. A remarkable thing about these cores is that interval between the two magnetic susceptibility peaks is largely laminated. I'm pleased to see that you can get a sense of the laminae here from an X-ray that came from our X-ray, our XRF facility. And I'm not terribly comfortable with searching for element pairs to find ones that give good-looking cycles. But that's what we did here. And I don't have, I don't have a strong reason to say that this means anything very profound, except that it seems to be correlated somehow with these laminae. And the grayscale is perhaps a better way to quantify the laminae, which is what you see here. And both of these records are smoothed by 9-point smoothing, and they have some features in common. What's interesting then is that this is only one section of the core, 1.5 meters, but we have an interval that's like 4 meters thick between, that's laminated like this between the two magnetic susceptibility peaks. And the sediment beneath the lower magnetic susceptibility peak is also laminated. This short interval here of about 1/2 meter is where we see the big ice rafting event, or there you go, ice rafting, the big, what I think is a flood event. And we see a minimum in manganese. Now, manganese in the Arctic is a good tracer for terrestrial input. And what we see in this iron to calcium ratio here, which is, you know, kind of arbitrary, is this big change that I think reflects a change in provenance. Now, in the Arctic, when we think of delta O18, it's pretty straightforward to think in terms of low salinity, or salinity, because you can see the surface salinity, especially in this region, is very low as anywhere in the Arctic. And the idea of low delta O18 events is not particularly new in the Chukchi Sea or the Beaufort Sea. There's been other people that have found similar events. And what we have in core 15 is a pretty good-looking late deglaciation record from high delta O18 to low delta O18. My x-axis is almost always going to be depth in the core, and this is O18, obviously, in pachyderma. But prior to some point late in deglaciation, we have this low delta O18 event, and then we have this sustained interval here where we have low delta O18. It's as low as it is today without any ice volume correction. And just a hint of an event here, but when we add this core, we have the same event in low delta O18 associated with the ice rafting, et cetera. And we've dated multiple levels within this core. We haven't gotten into this one because the 4M abundance is much lower. And the two events are approximately 12.8 and 11,000 radiocarbon years ago. The big problem, of course, is trying to calibrate. When you do that, it turns out the older event is more like 14,000 years. Now, I'm really convinced by the Merton results, and I'm convinced that the two events we see here are most likely associated with the two Merton events. And therefore, this is what we see, and if these are valid, if this is a valid interpretation, then there must have been some very large reservoir changes. We also made measurements on the benthic radiocarbon dates on the benthic forams, and interestingly, on average, the benthic forams are only about 100 years older than the planktonics in the Holocene and during deglaciation. And that kind of makes sense because as what we might consider to be pre-bomb radiocarbon in the interval of 1,000 meters to somewhere up here is the same. In other words, the Atlantic water is pretty well mixed. It all has about the same age today, and it seems to have had the same age back in the past. This is my concluding slide. I talked about the provenance change. Well, the 4Ms are really low. I don't think 4M carbonate is driving the iron to calcium ratio here. And the magnetic susceptibility doesn't change much across this interval, so I'm thinking that this is really a change in input of detrital carbonate. And that indicates a change in source that would be consistent with the flood from Glacial Lake Mackenzie. And what we can do is estimate the sedimentation rates in this deglacial interval based on the radiocarbon dates. And we had two dates that were the same, of course, so they give you an infinite age, which is adjustable. But what we are looking at here is sedimentation rates during the deglaciation of roughly 10 meters per 1,000 years. And that's remarkably high for continental slopes. And I think that plus all the other data, plus the plus what was going on land, points to the inescapable conclusion that approximately at the beginning of the Younger Dryas and the pre-boreal oscillation, there were two really large floods. And they are likely the cause of these events when that water and ice reached the North Atlantic. Thank you. It's great to be last and run over.
Any questions for Lloyd?
Peter.
All OSL dates precise is kind of an oxymoron. Their typical uncertainty is 10 to 15%. So consider that.
It was, yeah, the optical dates they're analytically precise. I think I mean, they're 13,000 years plus or minus 0.2 or something like that, which is pretty good considering. I think the bigger question is how accurate are they? Would you agree that the
Precision is very low on OSL dates. They might have beat it down by averaging number of days.
Yeah.
Many of those dates are not from Knockout, so it's not
Right.
really correct. The second question is, was the shelf exposed during was there a low sea level shelf exposure?
Well, I can't answer that directly, except to note that there are channels mapped on the shelf near Mackenzie that they think result from this flood.
So is there a possibility that sea level rise might influence shelf sedimentation?
Well, I think if that's true, you would have seen it at other locations, but the deglacial maximum input of sediment is as in all of our cores, is consistently around the Mackenzie and the region to the east, which would be consistent with Coriolis and, you know, water wanting to go to the right in the northern hemisphere.